I think we probably have everyone who's joining at the beginning with us. I'd like to just start off and thank everyone for joining us today. If you haven't seen me online before, my name is Sajan Yukamadiala. I'm the communications manager at Capricorn Power. And I'm pretty excited about today's session because it is, I think, for anyone who really likes to learn about how things work, especially kind of the nitty gritty into the Barton heat engine. It's especially for those who are engineering enthusiasts, I think. And today who's joining me is Rowan Doyle. He's the manager of R&D products at Capricorn Power. Hi, Rowan.
Hey, Sajania.
Hey, how are you? So just before we get started, I wanted to take care of a bit of housekeeping. And you'll see that you were muted upon entry, but at the end, after Rowan's done with his presentation, we will open this up for Q&A. And if you'd like, if you have questions, throughout, if you're worried about forgetting them, you can always use the Q&A or the chat feature in Zoom to ask us as we go. And then at the end, I'll ask Rowan the questions that everyone puts forward. All right, so Rowan, I think that you have a bit of a presentation about the Barton heat engine and kind of Capricorn's engineering journey for us today.
I do, thank you, Sajania. Before I do, I'd just like to pay my respect, to welcome everyone and to acknowledge and pay my respects to the traditional custodians of the land on which we're meeting. In my case, that happens to be the Wurundjeri people of the Kulin Nation, and I pay my respects to elders past, present, and emerging, and welcome to any Indigenous people who are joining us today. Yeah, I'd ask you to take a minute to think about the traditional custodians of the land on which you're sitting, and also really acknowledge that in terms of engineering and design, we stand on the shoulders of greats, and I'll talk about a couple of them today, but they hark back a long way as well. The engineering that was presented by the traditional custodians of the land on which we meet was pretty incredible at the time as well. So on that note, I'm going to launch into a bit of a presentation and discussion. So hopefully, with a little bit of luck and a little bit of the magic of Zoom, you can now see a picture of the Barton, the very first Barton heat engine. And we've titled this talk Reimagining Ericsson's hot air engine, and that will become clear why we're talking about that as we go. Before I do, in terms of the traditional of the elders, I would also like to welcome, I noticed on the participant list that Dr. Noel Barton has joined us, which is fabulous. So Noel, as I go, if there's anything that you would like to pipe up with, please unmute yourself and feel free to join in. There will be plenty of time for questions and answers for everybody else as we go. All right, so I'm going to talk a little bit about today, the technical journey that we've been on, and cover a little bit into the design of the Barton heat engine, the whys and wherefores. I'm not going to go into the really detailed nitty-gritty. I'm not going to give away any of our intellectual property, but hopefully we'll cover a little bit of enough to really help you understand the journey that we're on and the amazing thing that we're creating. Okay, so this image here shows the first Barton heat engine down in Geelong, which we built a couple of years ago, and I'll come back to that in a minute. Now, where am I going? I want to move forward. There we go. So I'm going to start off with the flow sheet. So what's behind the Barton heat engine is a really, really clever innovation, a process innovation that Dr. Noel Barton came up with several years back. Now, I want to paint a picture of several years ago. So Noel Barton's background, he's an incredibly talented mathematician. He worked for the CSIRO for many, many years. One of Australia's great minds, and also a great innovator. And Noel, as his career progressed, realised that we had a really, really big problem. And he, along with many others, realised this, but Noel felt that he was actually in a position to do something about it. The big problem being the challenge of climate change. And Noel realised that one of the things that is missing in solving this problem of climate change is a really effective, efficient way of turning heat into electricity. There's lots of heat around. There's lots of heat around. Lots of waste heat in industry. Heat from the sun. So we know how to capture the sun's heat really quite well, and at fairly low cost. Often the challenge is turning that heat into useful electricity at low cost and at a variety of scales. So this was one of the fundamental reasons that Noel set himself the task of designing a heat-to-electricity engine. And he came up with this flow sheet. In front of you, it looks fairly simple, and it actually is. At its heart, it's incredibly simple. We use air as the working fluid in our heat engine, and that gives us all sorts of intrinsic safety advantages. The system is closed loop, which means we're recirculating the air, which means we can get a pretty high power output. It's recuperated, which means it's high efficiency, and I'll talk about the recuperation a little bit. The Brayton cycle, it has been around for a long time. It's not that complicated, and it uses a piston and cylinder arrangement. Piston and cylinder, you've got, unless you're driving an electric car, your car has pistons in the cylinders, and it's relatively uncomplicated. And it gives the advantage of running with a piston cylinder arrangement is low losses. So Noel came up with this very neat flow sheet.
Rowan, I just have a question for you.
Yeah, fire away, Susanna.
Before you continue, I'm curious about why building this heat engine is such a challenge.
That's a great question. When you look at this flow sheet, yes, it's simple. Where it becomes challenging is that we've got to get hot air. So if I go back a few steps, well, not that far. If you look at the loop there, you can see there's a red loop, and that's hot air coming out of the heater. Our air is at about 450 degrees Celsius. We've got to get that hot air into an expander where we're taking this hot air and allowing it to get bigger, to expand, and to give up energy to the system, in our case, to give up energy to drive a crankshaft. We've got to get that into the expander at exactly the right time. That's really pretty hard. Now, if you're driving an internal combustion engine car, your car has valves that are operating hundreds of times a second to let air in at exactly the right time. In your internal combustion engine car, that engine has an average temperature just shy of 100 degrees. Ours has, at the hot end, an average temperature of 450 degrees. It's actually pretty challenging. So high temperature, fast, and we've got to open that valve at exactly the right time. So it's not easy. Now, Noel actually stood on the shoulders of giants. I talked about elders before. And when Noel began investigating his cycle, he realized that it was very, very similar, or quite similar, to a cycle that had actually been invented in the golden age of heat engines back in the 1830s, 1820s, 1830s. John Ericsson, pictured here, fabulous sideburns, and many other things, but he came up with what he called his caloric engine, with a very similar cycle to what we're working with. It used air as its working fluid. It had a regenerator, which is a bit like our recuperator. And he built many, many different heat to, well, not so much heat to electricity, but heat to motion engines. And one of them was put onto a, one of them was put onto a ship during the American Civil War and nearly had a fundamental impact on the American Civil War. Phenomenally high efficiency. It had some other problems, and there were things that they just could not solve at the time, which does bring us to the next slide. And a couple of years ago, Noel and Capricorn and us, we built the first of these new Barton engines. And this is it shown down in Geelong. It used Commodore engines at its heart. Why used Commodore engines? Because they were cheap and cheerful and available. And we converted 3 used Commodore engines, one into the compressor. You can see the compressor straight in front of you here. And that's it. Ooh, that's the compressor there. And there are 2 others behind Noel, which were the expanders. And it worked. It worked just. It didn't actually produce much in the way of power output. It had some significant limitations. One of the key ones is if you're driving an internal combustion engine car, I mentioned before, it sits at about 100 degrees Celsius, and that's because the cooling system, the water in the car engine, is designed to grab all that heat and take it away. And for us, that's really bad because that's loss of efficiency. There were a few other areas that were limitations, but we learned a heck of a lot.
Rowan, can you tell us, I mean, obviously we've talked a little bit about Noel, but can you give us more about kind of the story about why he wanted to build the engine in the first place?
Yeah, I touched on this, but I didn't explain it very well earlier. The original idea I mentioned was this problem of heat. There's plenty of heat availability and a huge desire to turn that into useful electricity, particularly solar thermal heat. So sun's heat gets concentrated, and if you've got lots and lots and lots of money and plenty of land, you can build a big solar thermal power station. You'll find that the cost of collecting the heat isn't too bad. The cost of turning that into useful electricity is actually pretty high, particularly at a small scale. So one of the aims that Noel set himself in designing his flow sheet was coming up with something that was scalable to a relatively small scale, doable. So you didn't have to build a Loyang sized power station to make it capital efficient. Does that cover what you're asking?
Yeah, I think so. That was good.
All right, so I'm going to now jump forward a bit from the Mark I engine to our current one. And so we set ourselves the task of building our first commercial engine. And we realized that a used Commodore engine wasn't the ideal basis for it. But one of the best things to base this on was actually an industrial compressor, a big industrial compressor. If you remember before, I talked about piston in cylinder. Some of these big industrial compressors have piston and cylinder arrangements. And we talked to a number of potential suppliers for big industrial compressors. We're just about to order one. And COVID hit last year, and the supplier stopped answering any calls. So suddenly we were in a bit of a bind. We were proceeding on our engineering and everything, and we didn't have the heart of parts of the wrong bit. The easy bit of this, in a lot of ways, is the centre part, the crankshaft. And if I jump back to here, you can see at the heart of this, the centre of this flow sheet is a crankshaft which turns, and that's where the mechanical energy gets turned into rotary energy and goes into a generator to produce electricity. So we looked around in a bit of a bind. We wanted a big industrial compressor, and it turned out we found 3 second-hand, not quite as big as we were hoping, but 3 second-hand compressors out of California. They're ex-US Air Force, and we got them for a pretty good price and imported them May-ish last year. And here they are being unpacked down in Geelong, and this is the first one. And so at the heart, there's a crankshaft, goes round and round. You can see up here, there's a motor that drives the crankshaft via a belt drive. And then on either side, there's what we call a throw, where there's a piston rod going in and out to a compressor housing. So we now had the basis for our heat engine, and we could perform our magic on it, perform our engineering on it, not quite our magic. The first thing we had to do, though, was check whether the elements of the compressor could withstand the pressures and temperatures that we had. So we had to take this heat engine on the right to bits, not heat engine, this compressor on the right to bits, and test it. And we did, oops, I'll go back to that. And we did, and unfortunately, the bits were not capable of withstanding the pressures and the temperatures that we were working with. The tests failed. So we found that essentially, and I can mark this up, all this bit here had to be pretty much thrown out, and we had to design and build our own. And that was an interesting realisation and a challenge for our engineering team. Fortunately, we were up for it. So jumping forward, hang on, how do I go forward? We've now done, we then went and did a hell of a lot of design work. We have, as I said, a fabulous mechanical engineering design team, and I'll talk about the other parts of the design team as well, which are also fabulous. This is part of the it's a 2D version of the 3D model of the overall engine. You can see in the middle, there's the crankshaft, that's the bit there. Up here is our motor, which is used as a motor to start the whole cycle going, and then it converts across and becomes a generator. On each side, we've got a throw, which is where the compression happens. So you've got a piston rod going in and out here, and out on the right-hand side, and a mirror image on the left-hand side. You've actually got the chamber where the compression happens, and another chamber where the expansion happens. So in our cycle, we're compressing air at the start. We then take that compressed air, it goes off to over the left-hand side of this picture here. We actually have a heater. The compressed air comes back hot, really hot, 450 degrees hot, comes back in through the red pipe and into the expansion chamber, where that hot air expands, gives up energy, and that energy is used for 2 things. The first one is the expansion process drives the compression process, and it gives up more than enough energy for that. So the remaining energy is given up through the piston rods into the crankshaft and out through the engine. Simple. So almost simple. So here's the, it's called a PHE7 engine or compressor that we bought. And here's our 3D model. And you can see, and I'll annotate this again here. I was showing over here before the compressor there. Right in the middle is the cylinder. There's a piston inside there that goes backwards and forwards very fast. And in each end, you've got a set of valves and a manifold. Now, the manifold is just like in your car. You have a manifold at the top of your engine. I'm talking about those of you who have an internal combustion engine. The manifold, all it does is it brings air in, and the valves then get that air into the cylinder at the right time for the process. Exactly the same with ours. On the left-hand side here, you can see here's our compressor manifold. In the middle here is our compressor cylinder. And on the right-hand side is actually our expander head and manifold. So it's actually pretty simple in a lot of ways. And you can see right there, there's the piston rod, and equally in here, there's the piston rod. Hopefully that's making sense. Okay, let's just clear those drawings. And a bit of luck, jumping, oh, one too many forward. So zooming in a little bit further, I'm just looking now at the compressor manifold. You can see through here, there's a little thing with lots of dots. That's some of our inlet and outlet valves for the compressor. And on the right-hand side, you've got our inlet and outlet valves for the expander. Okay, where are we up to? What's all this got to do with looking back and solving the problems that we had last time? So in the first iteration, I said we were losing lots of heat through the water jacket. In this case, we actually don't have a water jacket for the hot end. The green part that you can see here is actually going to be covered with insulation. So we're keeping all that lovely heat where we want it. We still have to have some cooling. So inside the brown part here, we've got a cooling jacket, and that keeps the bit where the piston runs in the cylinder at exactly the right temperature, but we actually end up not losing that much heat through the piston and through the cylinder. We now actually had to go about building it. Well, first we had to go about designing the detail, and I'm just going to show you, jump a little bit forward. And I mentioned before that COVID hit. So nearly all of the design we've gone through has been done over Zoom and Teams and all of those sorts of systems. So you can see some of the team here, particularly Noel on the right-hand side. I've thrown up in the middle one of our drawings. In fact, all of our mechanical design's been done in 3 dimensions in 3D CAD. And unfortunately, I didn't have any photos of our wonderful designers, our mechanical designers, but here are some of our terrific design team. Jumping back, one of the key things we had to do in the design was design this engine for, as I said before, really high temperatures, really high temperatures, but also close to those high temperatures, much lower temperatures. And we needed to be able to predict how that was all going to happen without actually building the thing and then finding errors. So we've been doing a heck of a lot of analysis, detailed analysis along the way. One of the core tools we've used is a thing called finite element analysis, and showing here are a couple of the plots that we got out of the tools. One of the fabulous things during this whole design effort has just been finding the capabilities that we've got here in Australia to do this engineering and then to do the build. And I'll show you lots of photos of the build later on. This is working with a local company based out near Notting Hill who do this sort of analysis day in, day out. And you can see some of the plots that their fairly sophisticated software has turned out. The next stage, what have I missed, Sejanya? No? Have I missed anything yet?
Well, I was kind of wondering, you were talking about the expertise that you're looking for, and you were impressed by everything in Australia. Could you kind of talk about what sort of expertise was needed to build this heat engine?
Yeah, that's a really good question. So at the start, a lot of detailed mathematical modelling, and that's where NOEL was just, it is an absolute gun. As we got it deeper and deeper into the engineering, a lot of this heat engine is mechanical engineering nirvana almost. It's really deep mechanical engineering. I showed at the start the image of the guy with the sideburns, Ericsson. The heyday of these heat engines was back in the 1830s, but they couldn't do the sophisticated design that's been required to actually, the metallurgy and the sophisticated design to come up with something that fits within a container. So Ericsson's engines were enormous. His cylinders were typically 3 meters across. That runs at the sorts of speeds that we need. So we're going to be running at 10 cycles a second, 600 revs per minute. Yeah, so the 1830s engineering couldn't do that sort of stuff. Our engineering team, yes, mechanical heavy. We've also got fabulous process engineer, Barney Bruce, who's on the bottom left-hand side. Ross George in the top left, who's our head of Ostend, one of our partners, an amazing mechanical engineer, and Sophie Bainbridge, who joined us a couple of years ago. Now Sophie's is our lead mechatronics engineer. So in fact, that then brings to another point. While this is a mechanical engineering nirvana in a lot of ways, it doesn't work without really sophisticated control systems to make all the right things happen at exactly the right time. There are a bunch of other people in the team, and I'm sorry I don't have everyone's photos. Having designed this, we had to get it built. And I mentioned that Australia's got this great design capability. The other thing which was just an extraordinary find was just what all the other capabilities from an engineering point of view were. We've worked closely with a couple of casting companies. So in fact, I'll jump back to here. You can see these pictures here. Each one of these large chunks is a big lump of metal, a big lump of steel. The one on the left, the compressor head, is a lump of steel that weighs 300 kilos. So it's all very well to design this on paper, but it's quite another thing to turn it into reality. And so we've worked with casting companies to work out how to cast these in steel. This is at a casting company in Coburg. Their technical capabilities have been phenomenal. I got to know Murray, the manager there, pretty well, and found out they're not just casting stuff. They're casting stuff in Melbourne and exporting to China, which is really quite cool. They're doing really high-end stuff. And this little video shows a little bit of our casting. So most of it's sped up a bit. You can see there's a big ladle here that's called a ladle. They've melted the steel. I've sped it up quite a lot. They don't normally walk quite this fast or move metal at 1,000 degrees quite this fast. They've poured the metal into the ladle, and this is a pretty sophisticated mix of metal. They're doing lots of testing as they go. Again, this is not real speed. And then you can see them pouring the metal into the molds that they've made. So we've done the design. They've then built a positive and then they create sand molds of the negative that's going to create in this case, the compressor heads. This was a phenomenal experience to watch this really happen. And while it all looks a little bit archaic and all that sort of stuff, these guys were highly professional, highly safe. Yeah, we've ended up, jump forward a little bit, that metal that was being poured in the previous slide, you can see here after it's been post-treated and shot blasted and all sorts of things. This is it at the machine shop. This is down at a machine shop in Geelong. And there it is on the machine. And on the right-hand side, you can see some of the detail of the compressor. It doesn't normally, when it's in operation, it won't have all that steel swarf in the bottom. But that's our compressor head with various bits drilled, bits cut, etc. So again, the capabilities of the local Australian manufacturers has been phenomenal and yeah, really good. Now the casting process was interesting and we learned a heck of a lot. It didn't always go completely to plan. So another bit, this brown bit, was our compressor cylinder. And that's our part of the 3D drawing ready for casting production. And the first time they built it, the casting design wasn't right. The original design's right, but the casting design wasn't right. This bit is pretty interesting. While it looks pretty boring, it's just a cylinder. It's got inside here is a watered gallery. And so if you think about the mold that had to be made to cast this in, it needed, thinking about the positives and the negatives, it needed a bit hanging in space to make sure steel didn't end up where the water gallery is. So they 3D printed in a sand resin mix. They 3D printed a kind of snake thing and then held that in space and then poured around it. Now, unfortunately, the first pour looked like it had worked, but when we took it to the machine shop, it had what's called porosity. It had holes in it. So we went on to the next pour with some changes that the casters made. So this was all part of the casting design rather than our design. And that didn't work either. They'd made some changes. It helped a little bit, but it had even worse problems, actually. And so that didn't work. The third time worked beautifully. And there's the two cylinders sitting on a pallet, and there's the cylinders down at the machine shop and on the right-hand side, looking beautiful, all ready for testing. So eventually we got there.
Rowan, I just have a couple of questions because if I had them, I assume other people might. I was wondering if you could share what exactly the compressor does for the heat engine and also the cylinder.
Yeah, okay, great. Thank you, Sajanya. So in your car, coming back, conventional car engine, you have pistons in the cylinders. What does the piston moving in the cylinder do? It compresses air in your car engine, and then when the fuel gets introduced, there's an explosion and it expands out and gives that expansion creates the motive force to drive your car. It's similar in ours, except without the explosion. It's because we don't put fuel into our engine, we just put heat in. So hot air comes in, that hot air is hot and compressed. All it wants to do is expand to get bigger. And inside this cylinder, there's a piston. The hot air pushes the piston. It has to be, the cylinder, as you can see, is beautifully cylindrical, and in fact, this is before it's had its final honing finish. So with very tight tolerances around it, the air can't get past the edges of the piston, so it pushes the piston. That pushing the piston then drives two things, as I said before. It drives the compression at the other end, and it also drives the crankshaft to produce electricity. Almost simple, not quite. Good question. At the next end, at the other end of the whole train drive, is our expander. So we have at one end our compressor head, where we let the air in to go through the compression cycle. Then we have the cylinder in the middle, and at the outer end we have our expander head and expander manifold. Now, I said before the expander's at 450 degrees. It's pretty sophisticated. So we've got a high-end materials here. We spent a lot of time on the design of this expander head and getting the materials right. It's a really interesting grade of stainless steel. So on the right-hand side of this image, you can see the expander design. That's the CAD, 3D CAD design ready for casting. On the left-hand side, you can see what looks a bit like a Dalek, perhaps, for the Doctor Who aficionado. No, it doesn't look like a Dalek at all. It looks like some Men in Black weapon. So that was the expander head straight out of the casting. The long bits you can see are what's called runners, where the molten metal runs into the casting. There's the same thing from a different angle sitting on a pallet. So then our casting friends need to take that fairly ugly looking thing and clean it all up, cut off all of the runners and other bits. So there it is, looking cleaned up. But then it also goes through a bunch of heat treatment. And so then they shot blast it to clean it up. The expander heads have then gone off to one of our machine shop partners. This one's in Heidelberg in Melbourne. And there's the system on the expander head on the machine, and there's the expander head on another machine nearly finished. So that was a pretty, I'm an engineer, I get excited by this. Hopefully some of you, I'm completely bored by it. Really amazing processes, capability right here in Australia. And that then, those three bits, I've shown you three key bits: the compressor head manifold, the cylinder, and the expander head. And together they make the main pressure containing envelope. Right.
Rowan, could you just share, I've heard of some of this before, but could you share some of the challenges in designing and developing the expander head?
Yeah, it was really interesting. A lot of it came back to the simulations. I shared before with you some of the finite element analysis modelling that we did of this system. Actually, I'm probably running a little bit behind time. I could show you that in detail, maybe if people ask questions later on. When we did our initial models, we realised that we had some areas of really high stress. So this high temperature that this thing runs at, one side of it, we've got hot air coming in at 450 degrees. The other side, we've got cooler air leaving at 300 degrees. So we've got quite significant temperature differences. Temperature differences do all sorts of strange things. You just think about expansion and contraction that you see just between, let's say you put something in your refrigerator. We've got to be able to cope with all of those stresses, and the initial materials that we tried just didn't work. We didn't build it, we actually modelled it in the finite element analysis. So materials science was a really interesting challenge for this project. And selection, and again, we've found that some fabulous capabilities here. One of the things I'm really looking forward to is where we've got an upcoming partnership with some universities and getting to know some of the awesome materials capabilities there for our next phase will be, as we optimise things into the future, will be really useful. Lots of other challenges along the way, but that was the materials one was quite a big one. Okay, so I've taken you through the heat engine mostly end to end. It's taken us a heck of a long time to do this. We've been working on this for months. COVID's really, COVID hasn't helped. I showed you us sitting around a table and on Zoom. It would have been easier to be all in an office, but the team have just done incredibly well. And these parts that you can see here are actually a bit further, quite a bit further advanced than what you're seeing on these pictures. And they're just about to be bolted together down in Geelong in our heat engine. And in fact, today, one of the things we have to do to these big parts is test them, not quite to destruction, but we have to do a thing called a hydro test where we put water into them, pump that up to a high pressure and just check for any major casting faults. And one of the main hydro tests was today, and it was fabulous to hear that that hydro test has passed with flying colours. Okay, the last thing I intended to touch about was the valves. So I mentioned earlier that it's really hard to get the hot air in and out at exactly the right time. And the valves to get that air in and out at exactly the right time are one of the key challenges with this heat engine. So we did two things with our valves. One, we designed them. Three things. We've designed our valves. We've designed them not to leak. That's pretty impressive. One of the other challenges we had with our Mark I heat engine was very leaky valves. And if you think about your car engine, the valve leakage is not a problem in your car engine. For us, any leakage of our hot air is a big waste of energy. So we can't have any leakage. And in fact, Rolf, who you can see there, in the second picture, pointing out a number, he's one of our key mechanical designers, and he came up with a brilliant design for how to seal the valves. We then we wanted to actually test these, not just simulate, but we wanted to actually build these valves at full size and test them and make sure they were going to work. So you can see here out at Notting Hill, in the depths of winter, our parts of our test rig. And we designed and built this using a hydraulic system, using a servo valve, really high-end hydraulics, to bang our valves backwards and forwards at 450 degrees. In fact, you can see Rolf there pointing out that it's things got to 450 degrees, and you can see Sophie masterminding a lot of the testing. Yeah, was great stuff, and that's really informed how our final valve design and operation. And that is all going to end up, not the valve test rig, but the whole system is going to end up shortly in this container, which is waiting for it down in Geelong. So I've tried to give you a really quick overview of the heart of the heat engine. As I said, the middle bit, the crankshaft and the lubrication, in fact, the very well-known stuff is an industrial compressor bought off the shelf, in our case, bought secondhand. And we got two others along the road, so we can build two more heat engines like that. And then the complex bit over the last 6 to 8 months has been designing and then getting built the compressor-expander assembly, or the complex bit for me, for the mechanical engineers. At the same time, our wonderful mechatronics and control systems team has been designing and building the control system that'll make this all run. And we're starting commissioning almost as we speak. And so really excited to see over the next few weeks this all come together and start producing electricity in the first of our commercial engines.
Thanks, Rowan. Before we kick off the rest of the Q&A, I just want to ask just so you can kind of contextualize this for everyone on the call, what does building this, you know, in this heat engine, this container, what does that mean for future projects for Capricorn?
Look, this is really just the start. So building this engine at this scale, it's exactly the right scale for us to move into, to connect it up with a pyrolysis unit, subject of future webinars, with future Capricorn webinars. We've got a pyrolysis unit identified and a source of feedstock for that. So the pyrolysis unit then produces two things. One is heat for the heat engine, and the second thing, it also produces biochar, which is, again, subject of future webinars, but a fabulous product for agriculture and for locking carbon in, so carbon negative. And yeah, at the same time, the pyrolysis unit produces useful heat that we're put into our Barton heat engine and produce electricity. So lots and lots of places we will bolt these in.
It's quite exciting. So I might launch into the first question. Do you simulate entire mechanism using software like Altair CFD?
Chirag, that's a good question. So we've simulated the entire thing in a number of ways. The first one's in a spreadsheet model. The second one is we have our heat and mass balances done in well, I can't remember the name of the software. Epsilon software. So the heat and mass balances is done in detail in that. We haven't done any CFD, any computational fluid dynamics at this stage, but we will do some of that in later stages. We've done a heck of a lot of simulation using finite element analysis. Where are we? Have we thought of expanding this great idea into Asia? We absolutely have and absolutely will. We will be, but we've got a whole lot of customers who are waiting for us in Australia first. Michael, would it have been way easier to transfer the heat into another substance that boils at a lower temperature? So different heat engines, good question. Different heat engines use different heat transfer fluids. We're using air as our heat transfer fluid, which has lots of advantages. It's intrinsically incredibly safe. Other heat engines use other heat transfer fluids and that have different properties. There are two big advantages with the one that we're using. It's free, and intrinsically really safe. The other advantage is the particular cycle that NOEL's designed is incredibly intrinsically efficient. So our ability to get the efficiency right up is there. What matter is used in this machine to produce energy? The thing that we're interested in is heat. So we take heat and we turn that into electricity. That heat can come from any source. As I said before, solar thermal is a great source. In the short term, we're working particularly with pyrolysis and to pyrolyze waste materials and turn those into biochar and heat. Do you lubricate the expander at 450 degrees Celsius? Short answer is we're using a fairly standard air compressor at our heart, and there are lube and non-lube air compressors. Hajir, how would we say Capricorn has pivoted around the problems COVID has presented? Now, that's a good question, Hajir. we have absolutely pivoted. We were going to, as I said, buy a slightly larger compressor base, and we've bought 3 slightly smaller ones. We had to learn at an earlier stage than we expected about some of the heart of what our engineering is that I've just been covering. So there has been a bit of a pivot there. Having said that, we're producing heat engines, they're reciprocating, the pivot's not that huge. Michael, are you thinking of making smaller versions for the bush? Great question. Short answer is we're planning to make a variety of sizes for lots of different places. Henry, current engine targeting 25 to 30% conversion of heat energy. I'm probably not going to go into that in that's R&D. I'm not going to go into today. The expectation is that we'll get 25 to 30% conversion with this engine. And yes, there are opportunities to go better than that, but at 25 to 30%, and this is actually an important point, at 25 to 30% conversion efficiency, we're already right up there in the world in terms of heat to electricity conversion rate. Anything, well, even at 25 to 30%, that's really, really exciting. So yes, we'll be looking to improve, but this is pretty cool. So Jania, when are we running the webinar on pyrolysis?
So I think we'll talk more about the Ostend Bioenergy project probably next week or the week after, but we probably only have time actually for maybe one more question just to make sure that it's just under an hour. I'm sure people want to get to dinner.
Do you want me to keep going through the questions?
So what about what's the power output? What power output is the unit under development?
So the initial power will be pretty low. It'll be about 15 kilowatts. So if you think, pretty low compared with an industrial power station, pretty high compared with the solar panels on your roof. That system has the capability of being what's called debottlenecked significantly, up towards 100 kilowatts. So our aim is to be in the next year or so having 100 kilowatts, maybe a bit more in a container, which will be again pretty exciting and very much a fabulous product from what all of our customers are asking for. Minimum temperature, Roger, for a system to be viable, we're really targeting medium grade heat, medium grade waste heat. We don't need thousands of degrees like a steam turbine, a coal-fired power station, but we're looking at around, I said 450 degrees. We can go a little bit lower than that, but from what we've seen, we don't need to. There are so many heat sources available for us in that range. Timothy, what's the next step after testing the current prototype? So we will be testing this, working with universities to look at longer term improvements, but then we'll be bolting it together with a pyrolysis unit and producing useful electricity into the grid and useful biochar. So that'll all happen, I expect, fairly rapidly. And what efficiency? I think we've talked about efficiency, 25 to 30%. Simon asked about the fuel source. So in our initial testing will be using gas for as short a time as possible, mainly because we really need, in our early stages of testing, to be able to turn it on and off rapidly. We'll then move into using pyrolysis of waste, particularly green waste that would otherwise end up in landfill and contribute to the, would otherwise be contributing significantly to the greenhouse challenge. What power output is the unit under development? I think I've covered that one already. What else haven't we? There's a couple of things on the chat. Use ceramic valves. We've looked extensively at valve materials. At the moment, we're not using ceramic valves. We may in the future. I have to say, valves are something that's really, really interesting. We have what we think is a really good solution. Are there opportunities for improvement from there? Absolutely. Anonymous attendee is saying that there are far more efficiencies to be gained by using steam as the heat moderator rather than air. So why are we not using steam? Steam turbines have been, steam engines have been around for a long time. Steam and water absolutely have some advantages. And air has the disadvantage that because it's a gas the whole time, getting heat in and out of it is a bit harder. Air has some phenomenal advantages. As I said before, the intrinsic safety is really significant. The ability for us to get our efficiency up is really significant as well at small to medium scale. And when I say small to medium, I'm not talking about domestic scale, I'm talking about industrial scale. So hundreds and even thousands of kilowatts. From a capital point of view, we are confident we'll be able to beat steam turbines hands down.
I think that covers off most of it. If there are any other questions that were left unanswered, we will get to them and send them out with this recording. I hope everyone enjoyed that as much as I did. Rowan, thanks again for joining us today. And thanks for everyone who attended on a Wednesday night. I know your time is precious, so we really appreciate it. And just again, if you haven't expressed interest in investing, please go to our virtual campaign page. And of course, always consider the offer document and risk warning before investing. Thanks so much, everyone. Thanks again, Rowan. Have a great night.
Thanks, Sajana. See you, everyone.